Okay, before we get into a quantitative coverage of reflection and transmission at oblique angles, I want to talk a little bit about Snell's laws. So, Snell's laws are um, basically the result of applying the boundary conditions for electromagnetic fields to boundaries between medium 1 and medium 2, with medium 1 having epsilon 1 mu 1 and medium 2 having epsilon 2 mu 2. So we have an incident wave that is traveling with direction of propagation k. It's incident upon this boundary, and a portion of the wave is reflected and a portion of the wave is transmitted. The reflected wave comes off at angle theta reflective, and the transmitted wave comes off at angle theta transmitted. And notice that the incident, reflected, and transmitted angles are all measured with respect to the perpendicular to the boundary, not the boundary itself. So basically what Snell's laws tell us is that the angle of incidence and the angle of reflection are equal. So this is Snell's law of reflection, and that the angle of transmission and the angle of incidence are related by the following expression, where the sine of theta transmitted over the sine of theta incident is the phase velocity in medium 2 over the phase velocity in medium 1. And then using the relationships between phase velocity and mu and epsilon, we can then substitute mu and epsilon, the material properties, so that we basically get transmission and incident angles as a function of the material properties only. So this is Snell's law of refraction. And as you can see, the transmitted and incident angles are related depending on the relative values of the material properties in media 1 and the material properties in media 2. And so the angle can either bend more toward the normal or more away from the normal, depending on whether media 2 has a higher or lower relative dielectric constant. Now, the index of refraction N, which is commonly used in optics, is basically defined as the speed of light over the phase velocity, which is mu epsilon over mu naught epsilon naught. And so basically the index of refraction is the square root of mu relative epsilon relative. So we could write actually then the transmitted and incident angles as a ratio of N1 over N2. So note that they are inverted. So transmitted angle is occurring in medium 2, incident angle is occurring in medium 1. So the indices of refraction is flipped in the fraction, just like mu and epsilon are. And now for non-magnetic materials, the sine of theta t over theta I is n1 to n2, or the square root of epsilon relative 1 to epsilon 2, which can also be shown to be eta 2 over eta 1. So there are then relationships for the index of refraction, the dielectric permittivity, and the impedance of the materials. Now, when the refraction angle is 90 degrees, then we call the corresponding incident angle the critical angle. So, for example, let's look at this figure. First of all, inward refraction means that when we're going from medium 1 to medium 2, the angle bends toward the normal to the boundary. So you can see theta transmitted here is smaller than theta incident, and this occurs when N1 is less than N2. So this is the classic case of going from air to glass, or air to water, or air to some other material that has an index of refraction that is higher. If the index of refraction is lower, so this would be going, for example, from water to air or glass to air, then the transmitted wave direction of propagation bends away from the normal. And you can see that in an extreme case, if theta incident gets large enough, theta transmitted then becomes right along the surface here and becomes 90 degrees. So we can determine that angle when we look at theta transmitted of pi over 2. We find that the sine of the incident angle for that to happen has to be N2 over N1. So that's referred to as the critical angle. It can also be expressed in terms of the relative epsilon when we're in non-magnetic material. And that then is the case of no transmission, which is a commonly used thing in fiber optic transmission. So in this example, we're looking at a light beam passing through a slab. So this is a simple example of we have a beam that comes in with an angle of incidence theta 1. It then becomes refracted in material 2 at an angle of theta 2, and then coming out the other end back into the same media that it originated in, it becomes refracted again at an angle of theta 3. So if we look at the upper surface, Snell's law determines a relationship for the upper surface that the sine of theta 2 is n1 over n2 times the sine of theta 1. At the lower surface, the sine of theta 3, which is the final angle, is n2 over n3 times the sine of theta 2. But in this case, n3 is actually equal to n1, and the sine of theta 2 was given by the previous equation. So we can substitute this top equation, n for sine of theta 2. We can substitute n1 in for n3, and basically we'll end up getting then that the sine of theta 3 is equal to the sine of theta 1, which means that theta 3 is equal to theta 1. So this slab of dielectric material displaces the beam's position, but it does not change the direction of propagation. And this is an interesting phenomenon because you can actually have any number of layers instead of a single material N2. You can have any number of layers of dielectric material, and it will have the same effect where the final direction of propagation is the same as it was before you entered the thin film or whatever this dielectric slab becomes, but it does displace it to the right in this case.